In the last couple of lectures, I focused on the fossil fuel resources coal, oil, and natural gas, where remember that oil is often referred to as petroleum. And the last lecture we talked about how we use distillation or cracking processes to separate individual hydrocarbon fractions in oil, something often referred to as fractional distillation. It's important to remember that at present, globally and in the United States, oil, natural gas, and coal account for a majority of the primary energy that we consume. And remember, there's a difference between primary energy and secondary energy. Primary energy is all forms of energy consumption for all purposes: planes, trains, automobiles, electricity, etc. Secondary energy is specifically electricity, where we're using fossil fuels to generate electricity that we consume. I want to focus today's lecture on two other fuels for electricity. The first is nuclear, where we use uranium, and the second is hydroelectric power, where we use the gravitational potential energy of water in streams or lakes. So if we look at the table on the left side of your screen, these are data for 2019. And just to give you a sense of how much electricity we're talking about in the United States, not globally, if you go back to your modules where you learned that currently, as of 2019-2020, DTE, or Detroit Edison, our local utility here in Southeast Michigan, they annually produce about 50,000 gigawatt hours of electricity that is consumed by me and others here in Southeast Michigan. If you look at the total United States electricity consumption, it's about 4,118,000 gigawatt hours. So we're talking about a significant increase from our local electricity consumption summed across the entire United States. And when we look at how across the United States that electricity is generated, you can see fossil fuels here top left, natural gas dominates, coal is currently second, and then petroleum is a relatively minor proportion of the fuels that we use to produce electricity. But if you look at the US as a whole, about 2/3, or slightly less than 63%, of all of our electricity that we consume across the United States and territories is produced by these fossil fuels. Nuclear here produces about 20% of all of the electricity consumed in the United States, and renewables as a category produces about 17.5%. And you can see that there are different types of renewable energy for the purpose of producing electricity. Hydropower I'll talk about today, and in the next lecture I'll focus on wind and focus on solar, including some discussion of photovoltaic, solar thermal, and geothermal. So today I want to focus on nuclear and I want to focus on hydropower. And remember, one of the themes of these last few lectures in the class is that if you imagine a world that is truly independent of fossil fuels, meaning that we don't use any coal, any natural gas, or any oil as a primary energy source, just for electricity, we have to replace this 63%, which is a significant amount of energy that needs to be replaced, by either nuclear plus renewables, or according to the new Green Deal, no nuclear, no fossil fuels, and all renewables. So let's talk about nuclear. Nuclear sits here. We currently produce about 807 billion kilowatt hours of electricity per year. And as I said, about 20% of the entire country's electricity comes from nuclear. If you look here at a timeline that I've shown you in a previous lecture, where we go from 1950 until about 2016, 2017, the black line at the top is coal. And you can see for probably the last 30 plus years, coal has been progressively declining. And then it's gone sort of off this cliff over here on the right. Whereas if you look in orange at natural gas, just as a reminder, natural gas has gone from about 10% of United States electricity 30 years ago to now in excess of 33%. So natural gas has significantly increased, coal has significantly decreased, and that is 100% driven by the economics of coal versus natural gas. If you look at nuclear, In 1950, there was no nuclear. By 1960, there was an incredibly small amount of nuclear. And then you can see starting about 1970, the growth of nuclear energy production in the United States. So nuclear is a relatively young form of technology that we use to produce electricity. And if you notice, since about 1990, it has remained steady at about 20% of U.S. electricity production. And you can think of this as a plateau for reasons I'll go into later in the lecture today. One of the things that makes nuclear so challenging in the United States and other developed countries and developing countries is that on a dollar-for-dollar basis, nuclear is very expensive. It's the most expensive type of electricity generation technology. Even though it has a very low carbon emissions footprint, it's very expensive. And without going into the details, that's just something to keep in mind that I'll come back to. So when we talk about nuclear electricity, we are focused on the element uranium, and specifically the isotope of uranium known as uranium-235. Uranium as an element has many different isotopes, and the isotopes are what we call radioactive. In the case of uranium-235, it is a fissile element, which means that it undergoes fission naturally, spontaneously. And I'm going to play a video now to show you what I mean by the concept of nuclear fission, specifically for uranium-235, and then I'll walk through it.
Nuclear fission is the splitting of a heavy element's nucleus to form two new elements with smaller nuclei. One of the most important fission reactions is that of uranium-235, which is used in nuclear reactors and atomic weapons. The fission of uranium-235 is initiated when a neutron traveling with enough velocity collides with the uranium-235 nucleus. The collision produces U-236, which immediately splits into two lighter elements such as krypton-91 and barium-142. The fission event also releases 3 neutrons and energy. The 3 neutrons are capable of initiating more fission events if they encounter a uranium-235 nucleus. If a sufficient or critical mass of uranium-235 is present, the reaction becomes self-sustaining, resulting in the release of massive amounts of energy in the form of heat, light, and ionizing radiation, an atomic explosion.
So let me walk back through this. And we're going to start here by looking at a uranium-235 atom. And I just want you to keep in mind the 235 refers to the total atomic mass, the number of protons and neutrons within the nucleus uranium, the electrons effectively having no mass that is measurable. And what happens when a neutron from outside uranium-235 is forced into the core or the nucleus of a uranium-235 atom is that immediately the overall number of neutrons increases within uranium-235, and that causes the new atom uranium-236 to become instantaneously unstable, and it disintegrates or radioactively decays or breaks apart. Now, if you can remember hearing about Albert Einstein and his famous equation E equals mc squared, what happens when the accelerated neutron is forcibly injected into the uranium-235 atom, creating uranium-236, that uranium-236 immediately radioactively disintegrates, and 2 new atoms, one of which is the element krypton, and the second is the element barium, they are formed, and 3 neutrons that were originally in uranium-235, they are released. Now, according to Einstein, E equals mc squared. So when this reaction occurs, the mass of krypton plus barium plus these 3 neutrons is less than the original mass in uranium-235 and uranium-236. So that means that energy is liberated during this radioactive decay process. These 3 neutrons then, they are free now in a nuclear reactor to interact with 3 more atoms of uranium-235, which then produces more krypton and more barium, And each of those 3 atoms of uranium-235, when it becomes uranium-236 and experiences radioactive decay, releases 3 more neutrons. So this is, in essence, a self-sustaining process where all atoms of uranium-235, each time they undergo radioactive decay or fission, they produce krypton plus barium plus more neutrons. And the way that nuclear power plants work, and I'll show you a video to highlight this, is that you start with a certain amount of uranium-235 at the beginning of electricity production, and then you routinely, every 1 to 1.5 years, have to replace more uranium-235, because once uranium-235 experiences fission, it is never again uranium-235. That is an irreversible process. Now, in terms of electricity, what makes this so important is highlighted here, as was shown in the video, where we have an atom of uranium-235, a neutron is absorbed into the nucleus of uranium-235, making uranium-236, which is instantaneously fissionable, meaning it breaks apart to produce barium and krypton, releasing those 3 neutrons. According to E equals mc squared, when uranium-236 disintegrates into barium and krypton and 3 neutrons, 1 atom of uranium-235 that we start with releases 202.5 million electron volts. So think about outlets in your house that might have 110 volts or 220 volts. 1 atom of uranium-235 releases slightly more than 200 million electron volts, which means that uranium is among the sources of energy that humans consume. It has the highest energy density of any fuel. So if you look at the photograph at the top, you can see a person's hand, and they're holding a pellet of nuclear fuel, and a typical pellet contains about 7 grams total mass, and it contains enough energy, or an equivalent amount of energy, in that tiny pellet that's being held here in the hand. It contains as much energy as 120 gallons of oil, a ton or 1,000 kilograms of coal, and 17,000 cubic feet of natural gas. So the takeaway message here is that an incredibly small amount of uranium-235 is equal to very large amounts of oil, coal, and natural gas. The history of nuclear energy in the United States, and globally for that matter, is a function of World War II. And I won't go into the details there, but if you've heard of things such as the Manhattan Project that ultimately led to the catastrophic destruction of parts of Japan during World War II, that scientific discovery during World War II that uranium-235 undergoes fission and disintegrates was ultimately used to build nuclear power plants that were used by the Department of Defense. And I'm not going to go into the details here, but I'd encourage you to look this up, and you can find great videos online. Currently in naval fleets and also in naval destroyers, so battleships, nuclear energy is used as the primary source of energy in these ships. And on the bottom you can see a cutaway of a nuclear submarine now used by many countries around the world. And in the back of the nuclear submarine you can see what's highlighted, the nuclear power pack. Now the reason this was done is into and after World War II, the way that submarines operated was a combination of diesel engines and battery storage. Now diesel, remember, is a fossil fuel. It's a specific hydrocarbon that we find in oil or in petroleum, and that diesel fraction is separated from oil. And the way that submarines would operate is they would have large amounts of batteries within the submarine. They would have to surface, meaning they'd have to be at the surface of the ocean. They would operate the diesel engines, which is a form of combustion. Diesel plus oxygen equals carbon dioxide plus water plus energy. And that energy would be stored in the batteries, and then the submarines could descend back below the water column. So in the late 1940s through the early to mid 1950s, the U.S. Department of Defense, working in collaboration with scientists at a variety of universities, they developed nuclear power plants that would fit within submarines. And today, the nuclear power plants in submarines allow submarines to stay underwater for more than 30 years. So when a new submarine is built, it typically has an anticipated lifetime of 30 years, and once it submerges, it would not have to come back to the surface to be replenished with new uranium-235 for at least 30 years. Around the world, there are hundreds of operable reactors. This slide here, I'll tell you, is a few years out of date. There are now more than 600 reactors around the world, and I'll come back and I'll highlight some of the challenges with nuclear, both within the United States and around the world. But I just wanted to give you a sense that in the U.S., I mentioned that nuclear provides 20% of our electricity. Globally, it's give or take about 10% of electricity around the world. So how do we actually access uranium? I'm going to give you a very high-level overview of the geologic environments in which we mine uranium as a resource. And I want you to picture granite, like the rock on the lower right side of your screen, which you can think of as a granite countertop that you might have seen either in your kitchen or someone's kitchen. Now, the rock granite contains a small amount of uranium, 10 to 20 parts per million uranium, meaning for each million atoms inside of a granite, 10 to 20 of those atoms are uranium, so 10 to 20 parts per million uranium. And when we look around the world, or here in particular in the United States, in the Rocky Mountain region, so this part of the western United States, much of the Rocky Mountains are composed of the rock granite. And what happens on geologic timescales, similar to the way that we discussed bauxite forming earlier in the class, rainwater percolates into the granite. Now remember, with bauxite, the way that formed is the rainwater percolates in and removes everything except aluminum. So by mass balance, aluminum builds up in concentration to form bauxite. In the case of uranium, the rainwater, which is slightly acidic and very oxidizing, it captures or dissolves uranium in the granite, and that uranium then becomes part of groundwater that flows below the surface. So on the lower left here is that map of the Rocky Mountains, and the image above here is a schematic of how uranium ore deposits form in geologic systems. And what I want you to see in the schematic is that we have what's called a clay confining bed at the top and a clay confining bed at the bottom. Those are referred to by geologists as aquicludes, meaning that water is not able to percolate through clay because clay is very impermeable. It has high porosity, but it has almost no permeability. And when that groundwater flows through granite and then moves into a geologic unit that might contain a lot of sand, that sand is very porous and very permeable, and that is what geologists refer to as an aquifer, where all of the pore space within the sand contains water, and that can be an aquifer that we could put a pipe into and we could build a well to use that water for agriculture or human consumption. In this case, as that water percolates through granite, the key is that that water initially, which was atmospheric water or rainwater, is very oxygen rich, and as I say in the text on the right hand side, when uranium comes into contact with very oxygen rich water, uranium is oxidized to uranium-6+ and is very soluble in oxidized, oxygen-rich groundwater. So that water moving through a groundwater system is able to transport uranium-6+, and as that water moves through our sandstone aquifer, if it eventually encounters a new type of rock that is not oxidized, or what we would say is a new type of rock formation that is reduced, meaning oxygen poor, that oxygen poor environment reduces uranium-6+ to uranium-4+. Uranium-4+ is not soluble in water, and as a result, uranium-4+ crystallizes or precipitates from the water to form a mineral such as the one shown here at the bottom center, uraninite, where this is a solid crystal that would now exist in this rock formation here, colored in red. So just to recap, uranium is dissolved by waters here off the left of the screen. It exists as uranium-6+ in groundwater. as that groundwater encounters a reducing front or a new package of rocks that is devoid of oxygen is reduced. Uranium 6+ is reduced to uranium 4+, and uranium 4+ crystallizes as uraninite. So how do we mine that uraninite? What we do today is we reverse that process. Historically, for the latter part of the 20th century, most uranium was mined either by open pit mines, similar to the Bingham Canyon mine, or it was mined by underground mines, similar to what we've talked about in previous lectures. What we do today, the broader we, is we essentially reverse the natural process. So the top here in the background is a photograph of a uranium mine in eastern Wyoming. And what you don't see is a pit, and you don't see an elevator shaft to go underground. The way the uranium is mined is on the left side. This is a photograph where there's a well, and the well injects oxygen-rich, oxidized water down into the subsurface. And just as what happens in nature, that oxygen-rich water oxidizes the uranium in uraninite, which is uranium 4+. It oxidizes that uranium 4+ to uranium 6+. And then the water is brought back up to the surface at another well. So the photographs on the right, what you can see is on the right-hand side are a column of wells that are injecting water into the subsurface, and on the left are a column of wells that are returning water back to the surface. So the way that we mine uranium is simply to reverse the process that nature uses to form uranium 4+ rich deposits. We pipe down water that has an oxidant in it, typically a benign substance such as sodium bicarbonate. That water plus the oxygen oxidizes uranium 4+ to uranium 6+, and the uranium 6+ comes back to the surface. So this is a schematic that shows that process, where we have in the center here, I'm tracing over a pipe or a well where we pipe down oxygen-rich water. And on the right-hand side, we have a pipe shown in red where water is returned to the surface. So that oxygen-rich water is piped down. As it moves through the rock that contains uranium 4+, it oxidizes uranium 4+ to uranium 6+. Now uranium 6+ is soluble in that water, and that water that now carries uranium 6+ is brought back to the surface. At these types of uranium mining operations, they have, as shown here, monitoring wells around the entire perimeter of the mine site, and those monitoring wells are also bringing water to the surface. And the reason is to constantly measure the concentrations of uranium to make sure that, as the arrows show, all of the uranium 4+ that's dissolved as uranium 6+ here is brought back to the surface, and there's no advection or dispersal of uranium into the surrounding parts of the aquifer, which would present problems for humans and other parts of the ecosystem. When that water is returned to the surface, it looks just like this here top left. Now it's referred to as something we call production fluid, where that fluid has been produced by mining, and that water now contains all isotopes of uranium. Now, of isotopes of uranium, there are 3 major isotopes. The most abundant by proportion is uranium-238, that constitutes about 99.3% of all uranium atoms. Uranium-238 is not fissile. So uranium-238 cannot be used to produce electricity in conventional nuclear power plants. Only uranium-235 is fissile, and uranium-235 accounts for about 0.7% of all uranium atoms in any particular sample in an ore deposit or in the production fluid. So each of the jars up here on the top, I'm not going to go through the details of, but there are proprietary techniques or chemical methods that the mining companies use to take production fluid that now has uranium 6+ dissolved in it, and by following a sequence of steps, ultimately produce something over here where the label says dried yellow cake. And the yellow cake is now solid uranium. And that solid uranium has this stoichiometry U3O8. all I want you to know here is that of all of the uranium atoms in that yellow cake, initially 99.3% are uranium-238, which cannot be used to produce electricity, and 0.7% are uranium-235, which is fissile and useful for electricity production. So what the mining companies then have to do, and this is highly regulated, is they have to take this U308 yellow cake, which again contains about 0.7% uranium, and they have to increase the proportion of uranium-235 and decrease the proportion of uranium-238. So it's in essence a zero-sum game for the total number of uranium atoms. But what we need in conventional nuclear power plants is we need more than 0.7% uranium-235 in order for a nuclear fuel pellet to produce electricity. So there are different ways that this can be done, and I'm going to highlight one here, which is referred to as centrifuging. And I want you first to look at the text on the top right, and I want you to think of a centrifuge as your top-loading washing machine at home. A washing machine, when you have it on the spin cycle, when it's trying to get all of the water out of the laundry, it typically rotates between 12 and 25 revolutions per second. That's the R over S. So think of your washing machine as spinning somewhere around 20 times per second. In a centrifuge that we use to separate uranium-235 from uranium-238, it is spinning at 1,500 revolutions per second. So 2 orders of magnitude faster than a conventional washing machine. Now, the text at the bottom tells you that uranium-235 and uranium-238 have about a 1% mass difference. And what happens in the centrifuge shown here schematically is, imagine the green is the outside of the centrifuge or the outside of your washing machine. It spins 1,500 times every single second. So the uranium is actually converted into a gas. Uranium-6+ is complexed with 6 fluorine atoms to make this uranium hexafluoride, and that gas is piped in here at the top into the center, and then there are in essence 3 outlets from the centrifuge, 1 in the very center and then 2 that capture the gas on the outside of both sides of the centrifuge. Now the centrifuge is spinning so fast that what happens within the centrifuge is uranium-238, because it's heavier, it is pushed to the outside of the centrifuge, whereas uranium-235, because it's lighter, it concentrates in the center of the centrifuge. So then the gas in the center of the centrifuge is extracted via this pipe in the middle, and that now allows an enrichment of uranium-235. And this here in the center is what is then used to produce nuclear fuel pellets. So I'm going to show you a video now of how a nuclear reactor works, just to give you a sense of what happens when that nuclear pellet is put inside a nuclear reactor.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of 3 crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron's speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with the fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reaction.
So this is not a class on nuclear energy, and I'm not going to hold you to much of what was in the video. I'll give you what I think are the highlights, but hopefully the video was somewhat interesting and makes nuclear reactors a little more transparent. This would be the nuclear core here, and we have these rods, and those rods contain the fuel pellets, and inside the fuel pellets we have atoms of uranium-235 that are fissionable. The rods are surrounded by water, and all of the little atoms here, think of those as the neutrons and energy that are being released during fission. That energy, or some proportion of that energy, will be absorbed by the water. So cold water is pumped in here at the bottom. That water becomes warm, and you can see the warm water then is piped out here at the top, and it goes into what we call a heat exchanger, where this pipe that I'm tracing over here, this pipe is all self-contained, so the water stays within that pipe, and then what occurs is inside the heat exchanger, this is a cylinder that contains water that surrounds this pipe that now has hot water. So cold water becomes hot by absorbing energy released during the fission of uranium-235. That now very hot water flows out of the nuclear core, and that heated water here loses its heat to the cold water here, which converts to steam. The steam is then piped out here. This is what we call a turbine, and that turbine spins like a fan, and that turbine is connected by a shaft to a generator, and the generator contains wires made of copper, and when the wires of copper spin in a magnetic field, that produces electricity. And I didn't go through the details in the lectures on fossil fuels, but in a natural gas power plant or a coal-fired power plant or an oil-fired power plant, the process is exactly the same as everything shown here, except natural gas or oil or coal are combusted to heat the water. So in this case, uranium-235, it's the energy that's released during fission that allows us to produce electricity. So this is just a schematic image of that video and what I just highlighted. And I don't need you to take away anything else on this video, on this particular screen here after watching that video. Now I mentioned the centrifuge, and the centrifuge is used to separate uranium-235 from uranium-238, so it increases the proportion of uranium-235. The reason that's important is shown here on this slide, where the bottom x-axis is the uranium-235 content, the percentage of all uranium atoms that are present in a particular fuel rod. And what you can see is that conventional nuclear power plants, they use fuel rods that contain 4 to 5% uranium-235. If you continue to increase the proportion of uranium-235 at about 20% uranium-235, so again, this would be 4 or 5, let's say 5% uranium-235, 95% uranium-238. Here we would have 20% uranium-235, 80% uranium-238. Those are used in what we call research reactors at universities and medical centers. If you continue to increase the proportion of uranium-235 to 90%, so 90% uranium-235, 10% uranium-238, that is the uranium mix that's used for nuclear warheads. One of the concerns around the world is that the y-axis here, think of that as the total amount of energy, centrifuging energy, needed to increase the uranium-235 to 5%. And notice that the difference between the amount of energy to go from 0.7% uranium-235 at the bottom to 5% uranium-235 here, to get to 90% is less than 50% more energy. So what you see in the news frequently is a lot of concerns about countries that do not currently have nuclear power programs. What might happen if a country develops a nuclear power program for the purpose of generating electricity? And could that country then develop nuclear warheads? So I don't show you any of these slides as right or wrong or good or bad, but this is a newspaper article from a couple of years ago. I believe I got this from the New York Times. Yes, I did. And this is one where the government in Saudi Arabia, they're interested in developing nuclear electricity because they recognize the need to increase electricity, and they don't want to generate electricity from the oil or natural gas that they produce. So what are the concerns of nuclear power plants as we currently know them? Among the concerns in the United States and in the European Union is nuclear power plants are getting old. More than half of all nuclear power plants in the United States are older than 30 years, and most of the remaining reactors, the other half, are at least 20 years old. Now, when nuclear power plants are built, they're initially designed for lifetimes of somewhere between 30 and 50 years, and they can actually last longer. They can go through a re-permitting or a re-licensing process, which is closely scrutinized by the federal government. But I just want to give you a sense here. If you look at the red triangles, each of those red triangles, all of the triangles here represent nuclear power plants. The ones in red are the oldest power plants. You can see very few power plants younger than 20 years. So remember that nuclear power generates about 20% of U.S. electricity. As these nuclear power plants age and eventually will have to be decommissioned, then another energy technology has to be used to produce new electricity to replace the nuclear power plant that is taken offline, referred to as decommissioning. The biggest challenge for nuclear power in the United States and the European Union is social license. This is a photograph of what is known as the 3 Mile Island nuclear power plant. It's an island here surrounded by water in a river. This is a nuclear power plant west of Philadelphia in the state of Pennsylvania. This here at the top you can read describes an incident on March 28, 1979, and for several days thereafter, where one of the 3 nuclear power plants here, nuclear power generators at 3 Mile Island, experienced a partial meltdown in the nuclear core. And this really was the beginning of ending social license for producing nuclear power in the United States. Then we had this disaster in the mid-1980s. If anybody has seen the 5 or 6 part series called Chernobyl on HBO, I saw it. I think it's a great series. My 15-year-old daughter watched it with me, and she also thought it was pretty captivating. But Chernobyl occurred only a few years after 3 Mile Island, and this is a disaster that occurred in the former Soviet Union, and it also was another nail in the coffin for social license. And I'm just going to play you a short video here if you haven't seen Chernobyl to get a sense of what happened and why people are concerned.
The world's worst civilian nuclear disaster took place when a reactor exploded at the Chernobyl power plant in Ukraine, then part of the Soviet Union. Present-day Belarus received 60% of the initial fallout. The radioactive cloud spread further to cover most of Europe. The Chernobyl nuclear power plant was one of the Soviet Union's most advanced facilities. The first 2 reactors became operational in the late 1970s. The 4th reactor was the newest, going online in 1983. On April 26, 1986, technicians prepared to test the backup cooling system in reactor number 4, but the routine safety drill went horribly wrong. A nuclear reactor is like a giant steam engine. Uranium fuel rods react to produce a massive amount of heat. That converts water into steam, which drives huge turbines to generate electricity. Control rods are inserted in between the uranium to slow the reaction. And it's crucial for cooling water to be pumped around the core to prevent overheating. But as the tests began, almost all of the control rods were removed, and technicians lost control of the flow of coolant. Temperatures soared, and extreme heat began to melt the core. At 1:23 a.m., Reactor 4 exploded. It spewed 8 tons of radioactive debris into the atmosphere. 115,000 people were evacuated from a 30-kilometer zone around the plant. The battle to put out the fires inside lasted for 15 days. More than 500,000 military and civilian personnel were drafted to deal with the accident and its aftermath. 31 of the initial firefighters and plant workers died within days from acute radiation sickness. The toxicity of the radioactive cloud was equivalent to 400 Hiroshima atomic bomb explosions. Crews hastily built a concrete sarcophagus to encase the entire reactor to prevent more radiation from spreading. Inside, there remained 200 tons of radioactive fuel. The remaining 3 reactors continued to operate due to energy shortages in Ukraine. It wasn't until the year 2000 that the Chernobyl complex was completely shut down. With the concrete sarcophagus crumbling, the international community began to build a new confinement structure for Reactor 4. It stands 110 meters tall, higher than the Statue of Liberty, and it's wide enough to fit a ship the size of the Titanic. At a projected cost of $3 billion, construction is scheduled for completion in 2017. One of Chernobyl's iconic red and white chimneys will be dismantled, and the massive steel dome will slide over reactor number 4. The confinement structure is expected to last for at least 100 years.
So this video actually does a little bit of a better job than the series Chernobyl. And I love the dramatic music. It's always amazing how great that is. But this failure of the reactor, and I was a kid when this happened and it was all over the news, this failure of the reactor is what literally scared the bejesus out of people around the world and caused the social license for new reactors to plummet. And as a result, not a single new reactor has been built since then in the United States and most other developed countries in the European Union. So then what's the third nail in the coffin was Fukushima. So if you look here at the image center, this is northern Japan, north of Tokyo. And if you look here, what happened at Fukushima was an offshore earthquake that had a magnitude of about 9. Now, the highest magnitude earthquake theoretically possible is a magnitude 10. So this is one of the largest earthquakes ever recorded or known by geologists to have occurred on planet Earth. And that magnitude 9 earthquake sent a massive tsunami towards the coast, towards Fukushima. And the Fukushima power plants here are right along the coast. So now if you look to the left side, you can see the 4 reactors, number 1, number 2, number 3, number 4. And what occurred is the failure of the backup cooling systems. So if you remember that video I showed you a few minutes ago, they described the need to have both moderator rods and also cooling systems. And the coolant here, the backup coolant systems failed, which caused explosions at the Fukushima power plant. And I'll show you in the bottom here a video that presents the explosion. So you're looking here, if I stop this for a second, you're looking in the background at, this is obviously onshore Japan. Here we have Fukushima and we have the reactors 1, 2, 3, 4. This is the Pacific Ocean in the background, and these are towers here that have electricity lines. And watch what happens as I push play. No dramatic sound on this one, but that cloud is literally a cloud created by the explosion of the nuclear fuel rods in the core of the reactors. Now, in addition to uranium-235, which is the fuel used for nuclear electricity, this also releases a phenomenal amount of additional radioactive material. And on the right-hand side over here is a map of radioactive iodine. And all I want you to see, if we focus in on this area on the right-hand side where the nuclear power plants were located, this is back to the comment, dilution is not the solution to pollution. That radioactive material that was blasted into the atmosphere has now contaminated a significant part of Japan in this area and has also been detected globally because we know the atmosphere convects material around the planet. Other challenges, and this is a map to highlight the challenges that Fukushima had here top right. So at the top we have nuclear power plants around the world built in earthquake zones, and on the bottom the green and red colors indicate areas that are seismically active, meaning there has been an earthquake since 1973. So if you look at all of the power plants here in Japan and other parts of Southeast Asia, and you look at some of the power plants here in the Mediterranean region, which is earthquake prone, there's a concern that the exact same problem that occurred at Fukushima could happen elsewhere. And that is what has driven social license close to zero in many countries. If we look around the world as of today, there are more than 600 operating nuclear power plants. There are about 60 or 70 new reactors under construction. And if you look at the map at the top, all of the reactors in black are ones that are currently under construction. I'll tell you these 3 in the United States here that I'm tracing over, those have now been abandoned and they're being converted to natural gas power plants because natural gas is faster and much cheaper to build. If we look at the inset on the bottom where I've blown up Asia and the Middle East, the majority of the nuclear power plants being constructed are in countries shown here either in the Middle East. There are a number being built in India. some in Russia, several in China, South Korea, and other parts of Southeast Asia. One of the challenges, again, is that nuclear power generates 11% of global electricity, and it's not so much how many nuclear power plants an individual country has. So if we look here at the schematic on the left, these are the number of reactors as of last year in each of these countries. But if you focus on the image on the right, you can see that, for example, in France, about 75% of the entire country of France's electricity is nuclear electricity. The Ukraine is close to 60%, Slovakia close to 60%, Hungary close to 55%. So if nuclear power ceases to be an electricity resource, then something else has to produce that electricity. The last nail in the coffin, just to re-highlight something I mentioned earlier, is cost. It is prohibitively expensive and on average takes more than a decade to build and flip the switch on a nuclear power plant, which means that companies cannot get approval for these as business plans in most countries around the world. The places where you see nuclear reactors being built, they are largely financed by the government of those countries. So that is the high-level primer on nuclear power. In the second part of today's lecture, I want to talk about hydroelectric. Hydro meaning water and electric meaning electricity. And down at the bottom here, I've highlighted hydroelectric. And again, I want to make the point that this is for the United States, not globally. In the United States, if we go back to 1950, about 30% of our electricity was from hydroelectric. Today, it's about 6%. So the amount proportionally of electricity we get from hydro is decreasing and at best plateauing over your lifetime. Hydroelectric is also a relatively expensive way of generating electricity, and it has a number of negative impacts on the environment that also have led to a decreased social license to build new hydroelectric in most countries around the world. So where does hydropower come from? In the second grade, if you grew up in the state of Michigan, you learned about the water cycle. And all I want to do is just remind you that the water cycle is one where incoming sunlight warms up the ocean water evaporates, the ocean water that's evaporated comes over land, falls as precipitation, and flows back downhill towards the oceans. That's the water cycle in a nutshell. And that's how we use the water cycle to generate electricity. The water cycle is driven by solar radiation and gravity. If we think of rivers throughout the United States or throughout the world, all rivers flow downhill, and anywhere that there is a topographic gradient or downhill, anywhere there's a river, we can use that water to generate hydroelectric power. We've done it for hundreds, if not thousands of years. Shown on the left is a water wheel that's a water wheel that's several hundred years old. And water wheels, as you can see on the schematic on the bottom, take advantage of an artificial topographic gradient where water comes in what's called the mill race, falls on the wheel, it spins the wheel here, and that wheel is connected to a shaft, and that shaft in this case rotates these stones, and this has been used to grind grain or to stamp batteries or other things for hundreds of years. What I'm going to focus on today is the use of rivers and hydro power to produce electricity. So this is a schematic that shows you the number of dams constructed in Connecticut, Massachusetts, New Hampshire, and Vermont over the last 150 years. Part of this gives you an indication of the concept of westward expansion or the growth of the European immigrant class as they displaced indigenous communities. And again, I want to make the highlight here that each one of these red dots is a dam that was constructed for the purpose of doing work for humans. So part of the theme of the last few lectures. And notice that each of the red dots is on a river, and it's on a river because that's where water is flowing downhill. So when we think of dams, I showed this image in a previous lecture when we talked about tailings ponds and dams for tailings ponds. This is the Hoover Dam, and on the top of the photograph is the Colorado River, which is flowing from behind your screen into the front of your screen. So the Colorado River here is dammed by the Hoover Dam. This creates what we call head, H-E-A-D, which I'll come back and define, and increases artificially the topographic gradient. And the dam is built such that water flows from high elevation here through the dam to low elevation, and at the bottom, that gravitational potential energy from the water that's flowing down this artificial hill is what we use to generate electricity. So I'll play a video now of how this process works.
Hydropower. Hydropower, or hydroelectricity, refers to the conversion of energy from flowing water into electricity. It is considered a renewable energy source because the water cycle is constantly renewed by the sun. One of the first uses of hydroenergy was for mechanical milling, such as grinding grains. But today, modern hydro plants produce electricity using turbines and generators. The mechanical energy created by moving water spins rotors on a turbine. This turbine is connected to an electromagnetic generator which produces electricity when the turbine spins. There are two main types of hydroelectricity production: dams and run-of-river. Hydro dams utilize the potential energy from dammed water to produce electricity. A dam is a large barrier constructed to raise the level of water and control its flow. The elevation created by the dam creates gravitational force for turning the turbine when water is released. Some dams also contain an additional reservoir at their base where water is stored to be pumped to the higher reservoir for release when electricity is in demand. This is referred to as pumped storage hydro. The second form of hydroelectricity production is run-of-river hydro. Run-of-river still uses turbines and generators, but relies on natural water flow rates of rivers, diverting just a portion of the water through turbines. Because run-of-river hydro is subject to natural water variability, it is more intermittent than dammed hydro. There are various sizes of hydro plants that produce electricity. Large hydro, greater than 30 megawatts, small hydro, 100 kilowatts to 30 megawatts, and micro hydro, less than 100 kilowatts. The Hoover Dam in the United States is a whopping 2,074 megawatts, which is enough to serve 1.3 million people. Of all renewable energy sources, hydropower holds the largest share of worldwide electricity production. Hydropower has several benefits. It is a cost-competitive form of electricity, even though the initial building cost can be high. It is quite reliable compared to other renewable options and pairs well with other sources as it can be used as baseload power. In some cases, dammed reservoirs can also help with flood control and be a reliable water supply for communities. There are also some concerns with hydropower, especially when it comes to large dams. Damming a river has a major impact on the local environment, changing wildlife habitats, blocking fish passage, and often forcing people in riverside communities to move out of their homes. In addition, dam failures can be catastrophic, claiming the lives of those living downstream. Hydro plants are also not completely free of greenhouse gas emissions. As with most forms of energy, carbon dioxide emissions happen during construction, particularly due to the large quantities of cement used, and plant matter in the flooded areas makes methane, another greenhouse gas, as it decays underwater. That's hydropower.
So a couple of things I just want to go back and highlight that they mention here. One is the concept here of baseload power. Baseload power means that you can use it 24 hours a day, 7 days a week, 365 days a year. It doesn't care if the sun is shining or the wind is blowing. So as long as you have water upstream, you can generate hydroelectric power. That's also how we describe natural gas and coal and oil and nuclear. They're baseload power because they work independent of the local weather. Now this is a schematic of a hydroelectric power plant. On the right-hand side over here is this word head that I introduced a few slides ago. And all I want you to see here is that on the right side of the slide, we've got a dam. Upstream of the dam, we have a lake or a river. And notice that downstream of the dam, what we call the downstream outlet, the level of the water is much lower than it is upstream of the dam. That vertical distance we refer to as head, and it's measured in feet or meters. One of the things that we know with respect to hydroelectric power, and I'll show you the equation in a few slides, is the larger the head, meaning the larger the distance between the top of the water on the upstream side of the dam and the downstream side of the dam, the larger this value of head is, the more power we can produce. So in the case of a hydroelectric dam, the water is allowed to move through the dam through a pipe referred to as a penstock, where it rotates a turbine, and that turbine turns a generator, and that is what pushes electricity out onto the grid that you and I use. So remember, in a nuclear power plant or natural gas or coal-fired power plant, we're using energy from those fuels to convert water to steam, and that steam drives the turbine. In this case, it's simply the gravitational potential energy of water falling through the penstock that turns the turbine. So this is here the equation I mentioned. The power, or the watts, that can be produced from a hydroelectric dam are the head, this vertical difference in height, times the flow rate times gravity, and flow rate is given in terms of units of water per time, so liters per second or cubic meters per second, and then the acceleration of gravity is a constant, 9.8 meters per second squared. So gravity is a constant, and what is done is to build dams so they have as high a value of head as possible, and then you can control the flow rate so you can increase head and increase flow to increase the electricity production. And typically at hydroelectric dams, there are multiple turbines connected to multiple penstocks. So you might run one at a time, two at a time, three at a time, four at a time. So in terms of that concept of baseload power, you could produce maximum power during the evening hours in July when everyone has their air conditioners on in Chicago, and then you can reduce the number of turbines that you use in the middle of the night when everyone's asleep and no one is using their air conditioners. There are different types of dams, and I'm just going to give you a high-level overview of those here. An impoundment dam, the word top left, is where you completely block the river. So if you look at the image on the right, we're looking at a lake that forms because all of the river now has been blocked, and only water that comes out of the dam is allowed to flow downstream. On the left-hand side are two images in an area of China where the Three Gorges Dam was built. In 1987, there was no dam. In 2006, the dam was under construction, and you can see that more of the area is underwater because when the river is dammed, it floods the upstream portions of the area. This is what we call a run-of-river dam. It's the Itaipu Dam in Paraguay. So top left is the inset here, South America and Paraguay. And it's called run-of-river because the river is on the left upstream side of the dam. On the left side here, the water is always allowed to flow. It's never stopped. And on the right-hand side is the actual hydroelectric dam, where electricity is produced and water flows down through each one of these penstocks. The one mentioned in the video, this diversion or run of the river, all I want you to think here is small scale. So here we might have a stream like the one shown in the center, and often case run of the river is built by building a pipe, for instance the one I show here on the right hand side in the photograph, where you don't have a reservoir, but you allow water from the stream to enter the pipe, and on the left-hand side that pipe carries the water down into a powerhouse where it spins a turbine to generate electricity. In the United States, there are almost 1,500 hydroelectric power plants, and they generate about 7% of the nation's electricity. And where you tend to see them is where you have natural topography or gradients in elevation. So you see here, if we look at the Pacific Northwest, Washington, Oregon, Idaho, very mountainous states, more than half of their power comes from hydroelectric. If we look at California, a large state with a large population, As much as 25% of their power comes from hydroelectric. And then we look at other areas, for example, South Dakota, Montana, and then here we have Tennessee, and up here in the Northeast we have Maine, and we have other states in New England that produce a lot of hydroelectric power, such as New York and Long Island. Among the challenges, I mentioned social license for nuclear power. One of the biggest pushbacks from the perspective of social license is that when dams are constructed, and these are all dams in squares here in the Pacific Northwest, they interfere in this particular region with salmon who spend their lives in the ocean and then swim back upstream to spawn. The dams block those salmon from moving back upstream. Now, worldwide, in our lifetimes, hydropower has grown. So in the United States, it effectively plateaued in your lifetime, and we haven't seen any significant new hydroelectric power. As the video mentioned, hydropower produces more renewable energy than any other renewable source. And what we do see is this growth, and that's because around the world there are specific areas that are building dams and increasing the amount of hydroelectric power. So on the top here, we've got a histogram for the years 2015, 16, 17, 18, and 19. The yellow is capacity additions for solar. The blue is capacity additions for hydropower. And the wind is capacity addition here in gray. New capacity means new gigawatts that are being produced, newly built infrastructure. And I want you to see that there has been a small amount of increased hydroelectric power worldwide, but not significant. Not nearly as fast a growth rate as wind plus solar. And you can see that on the bottom over a longer time scale from 1965 to 2011. It's been relatively flat, although we do see a slight increase in certain regions of the country. Again, here are just more data from 1990. These are data from 1990 to 2019 that are used to forecast how much hydro will grow over the next 30 years. And you can see that a small amount of hydro growth is forecasted, but wind and solar, which I'll talk about in the next lecture, are expected to grow much faster. This is just a snapshot of places around the world that are building hydroelectric, and right now China is building more hydroelectric capacity than any other country in the world. We have hydroelectric in our own backyard. So in the city of Ann Arbor, on the Huron River, there were 4 dams, or there are 4 dams, and all 4 were historically used to produce electricity. 2 of them now, Barton and Superior, continue to produce electricity. So what are other ways to capture hydrothermal electricity, or capture and convert hydrothermal energy to electricity? One is known as tidal energy, and I'll show you, this is a photograph here of an area in northern France, and I want to focus your eyes here in the center on the bridge. That bridge sits on top of a tidal energy electricity production plant, and you'll see how that works in this video.
Tidal power. Tidal power is a form of hydropower that converts the energy from the natural rise and fall of the tides into electricity. Tides are caused by the combined effects of gravitational forces exerted by the moon, the sun, and the rotation of the earth. Tidal plants can only be installed along coastlines. Coastlines often experience 2 high tides and 2 low tides on a daily basis. The difference in water levels must be at least 5 meters high to produce electricity. Tidal electricity can be created from several technologies, the main ones being tidal barrages, tidal fences, and tidal turbines. Tidal barrages are the most efficient tidal energy sources. A tidal barrage is a dam that utilizes the potential energy generated by the change in height between high and low tides. This energy turns a turbine or compresses air, which in turn creates electricity. Tidal fences are turbines that operate like giant turnstiles, whereas tidal turbines are similar to wind turbines, only underwater. In both cases, electricity is generated when the mechanical energy of tidal currents turns turbines connected to a generator. The generator produces electricity. Ocean currents generate relatively more energy than air currents because ocean water is 832 times more dense than air and therefore applies greater force on the turbines. Tidal power is easy to install and renewable, having no direct greenhouse gas emissions and a low environmental impact. Because the ocean's tidal patterns are well understood, tidal energy is a very predictable energy source, making it highly attractive for electrical grid management. This sets it apart from other renewables that can be more unpredictable. However, adoption of tidal technologies has been slow, and so far the amount of power generated using tidal power plants is very small. This is due largely to the very specific site requirements necessary to produce tidal electricity. Additionally, tide cycles do not always match the daily consumption patterns of electricity and therefore do not provide sufficient capacity to satisfy demand. That's tidal power.
So what the video shows you here
often experienced
is we're taking advantage of low tide and high tide. So as long as you've got a 15-meter difference between high tide and low tide, if we look at the tidal barrage, notice what's happening here. The water comes in and spins the turbine, and the water comes out and spins the turbine. So this works essentially 24/7, 365, where the water comes in, rotates the turbine in one direction, which we can use to produce electricity, and then when the tide goes out, it rotates the turbine in the opposite direction, and we can produce electricity. So tidal electricity works extremely efficiently as long as you have a high enough difference in the tide and you have a sustainable tide. Another type of hydroelectric power, which was referred to in the first video, is known as pumped storage. And pumped storage operates where we have a lake at high elevation and then we have a lake at low elevation. And the way pumped storage works is during the day when energy costs, meaning the electricity costs, are higher, the water flows downhill and it turns a turbine to produce electricity, and then the water is captured in this low lake. And at night, electricity is used when electricity is cheap. The energy company uses electricity to pump water back up to the top where it stores it in this high lake. And that's done using turbines that are reversible.
Australia has a big challenge ahead with its energy supply. Almost 3/4 of Australia's energy comes from coal, which will decrease in coming decades as coal stations close down. We'll need huge amounts of new energy generation to replace it, and renewables such as wind and solar are the cleanest and cheapest option. That's where Tasmania can help. We're looking at the potential to double Tasmania's electricity generating capacity by changing the way we use our existing hydropower system and by adding pumped hydro storage to help fill the gap when the wind isn't blowing or the sun isn't shining. Normal hydropower is created by storing water on high ground and running it downhill to spin a turbine at the bottom. Once the water's past one or more turbines, it flows on out to sea. Pumped hydro captures and stores water in two places with a steep drop in between. Water can be pumped uphill to reuse for power generation again and again. Of course, that pumping consumes electricity in itself. That's where wind and solar power come in. Pumped hydro, wind and solar complement each other beautifully, providing a stable, reliable, clean energy system. When the wind blows and the sun shines, but people aren't using much power, excess wind and solar power is available to pump water back up into storage. At other times, when the wind and sunlight aren't generating enough power to meet demand, the pumped hydropower system swings into action and makes up the shortfall. The whole system works together like a giant renewable battery, providing the storage, reliability and flexibility that wind and solar can't offer on their own. Tasmania has lots of steep hills that were perfect for building hydro over the past century and are ideal for developing pumped hydro today. All this new electricity and storage would put Tasmania's energy security beyond doubt and help give Tasmanians the lowest possible power prices. And by adding pumped hydro to one of Australia's only big hydropower systems, we can build it quickly and cheaply compared to other places, even when you add in the cost of more interconnection to get our energy to where it's needed interstate. That's why Tasmania offers the stable, reliable and affordable clean energy solution that Australia's going to need.
Okay, so obviously pro-Tasmania, but if we just back up here, one of the things that advocates of pumped storage highlight is, as I mentioned, during the day when energy prices are high, meaning they can sell the electricity at higher rates, the water flows downhill, turns turbines, and they produce electricity. At night, when electricity prices are lower, they use electricity to pump the water back uphill. Now that means you do need electricity at night, so if you partnered this with wind, where on average around the world wind speeds are higher at night than they are during the day, and possibly during the day with solar, then those would be inexpensive ways to generate the electricity to pump the water back up. In the United States, in particular in Michigan, electricity from nuclear power plants is used at night to pump water back up into storage facilities. And this is the one in Michigan that's one of the largest in the world. This is one in Ludington, Michigan, which is on the shore of Lake Michigan on the western side of the state of Michigan. And the way that it works is during the day. So this is the pump storage here that I'm tracing out. During the day, water is flown downhill and it's used to produce electricity. And the water flows out into Lake Michigan, shown here in the bottom of the photograph. And then at night, they reverse the turbines and they pump the water back up into the storage facility. So in essence, think of this as a battery. And the way that the battery works is you can look at it here on a 24-hour time scale, where we're looking at power distribution over a day of a pumped storage hydroelectric facility. Green represents the power consumed in pumping, and the red is the power or electricity generated and sold to customers on the grid. And what you can see is that typically late at night, let's say 11 o'clock at night on the right-hand side, through midnight to let's say about 6 a.m., there's a lot less power being consumed. So that's when the pumps are spun in the backwards direction and water is pushed uphill. And then during the day, when electricity prices are higher and consumers are using electricity, then the water flows downhill to produce electricity to sell onto the grid. This is just a snapshot. Here's Ludington, I mentioned, in the state of Michigan, on the western side of Michigan, on the shore of Lake Michigan. There are lots of these types of pumped storage facilities in the U.S. that we think of as batteries because that's how they operate. So the last bit of the lecture here, I want to just talk about some of the environmental impacts. One is structural failures. So this is an image of an earthen dam in the Teton Mountains, and you can see the dam here failed, which was catastrophic downstream because not only did the water flow downstream, but all of this sediment or the mud that had built up on the upstream side of the dam, it all flowed downstream as well. During periods of drought, dams can go completely dry. So here's a dam in Eritrea in Eastern Africa. You can see a G-pier for scale and people standing on the dam. In this case, during a drought, the entire upstream side of the dam experienced sedimentation, and now there is no water to operate the dam. They also have impacts on the aquatic ecosystem. So this again is the image of the Hoover Dam outside Las Vegas, where the Colorado River flows downstream through the penstocks to generate electricity. In the inset on the left-hand side, the Hoover Dam is right here. So here is the Hoover Dam here in Lake Mead. And I just want to highlight that that Colorado River that flows ultimately from the headwaters in the Colorado area, as that water is stopped here at the Hoover Dam and many other dams along the way, including Lake Powell and others, the amount of water and sediment flowing downstream decrease, and that has an impact on ecosystems downstream. I mentioned the Three Gorges Dam in China. One of the other effects also is this concept of human displacement. When you put a large impoundment dam in a river and you create a large lake on the upstream side of the dam, that floods large amounts of Earth's surface. And as a result, in China, close to 1.5 million people were displaced by construction of the Three Gorges Dam. So it has a negative impact on local communities. It also has a major impact on the local ecosystem, and that's I'll highlight here. Back to this dam in Paraguay. This is what the dam looks like now. This is what the area looked like before the dam was constructed. So this is what you would have seen if you had gone to this area in Paraguay several decades ago. this is what you see now. So truly devastating impact by this dam in this part of Paraguay. Biodiversity is also affected, so I won't go into the details of legal cases that have been fought over this, but there have been lots of lawsuits where environmental groups have sued the federal and state governments, the Army Corps of Engineers who were involved in dam construction and maintenance, because the biodiversity loss has been significant. There have been attempts, I mentioned a challenge of dams in the Pacific Northwest is they eliminate the ability for salmon to swim upstream. So there have been attempts to build what we call fish ladders, where in this case, if you look at where I'm tracing with my laser pointer here, these are ladders where salmon are supposed to find their way into the ladders, and then this is almost like a conveyor belt in some way for the salmon to move up and above the dam and to continue their swimming upstream to spawn. So with hydroelectric power, among the things that people really like is that after you build the concrete structure, there's effectively no greenhouse gas emissions. They're considered renewable. They have a very high conversion efficiency, which I didn't touch on and won't test you on, meaning of all of that energy in the water, the gravitational potential energy, about 80% is converted to electricity. Think about what we talked about with coal. You can use it for baseload power, 24/7, 365. You can also use it as a battery, pump storage. You can also scale it. You can have small dams, medium dams, large dams, and really large dams. And they're inexpensive to operate, and they last for decades and decades and decades. The negatives, though, on the con side, is that when you build dams, they change or involve loss of habitat. They displace people. In areas like the dam I showed you in Eritrea, climate change and the impacts of climate change on precipitation patterns and snowfall patterns can have an impact. They have high overnight capital costs, so something you worked on now in a recent module, those initial capital costs, and they do take a significant amount of time to construct. So lots of extremely good pros, but certainly cons, and the cons have caused a lot of people to not provide social license for their construction. The last slide here, just to highlight among all the electricity technologies we've talked about so far, in terms of their overall greenhouse gas emissions, hydroelectric is the lowest. So on a per kilowatt hour basis, this is CO2 equivalent in grams. Hydro is 4, nuclear is about 16, so also very low because once you construct a nuclear power plant, there are no ongoing emissions. If you compare that to natural gas and oil and coal, this is what the new Green Deal wants to get rid of. The new Green Deal is not a proponent of nuclear, but is a proponent of hydro and wind and solar and these other forms of renewables on the bottom. So I hope today I've given you a good idea of how nuclear fuel and how hydroelectric are used to produce electricity. And in the next lecture, I'll focus on wind and solar.